Okay, so dear colleagues, the title of my presentation is Failure Criterion for thread-like fibers in thermoelastic medium. So greetings from Ukraine. So, composite materials are widely used in modern mechanical and aerospace engineering because they are lighter, stronger, cheaper than traditional materials and can perform different in different directions. So this means that they are anisotropic. Therefore, there is also a wide scientific interest to the mathematical models and methods that allows evaluation, optimization, and design of their macro and micromechanical properties. Since one dimension of a fiber is much bigger than the other two, special models should be used to perform calculation of thermal and mechanical properties of the overall composition and to determine stress field near inhomogeneities. Nevertheless, binary model requires strict mathematical substantiation, since coupling of 1D and 3D boundary value problems results in an ill-posed problem, which solution requires introduction of special regularization parameters. The issues on fracture of such composites also should be studied in details. So we have the following boundary integral equations. The one is for heat conduction, and the other one is for thermoelasticity. So this integral equations, boundary integral equations, were obtained in the following work: Pasternak, Pasternak, Iaroslav, a comprehensive study on Green's functions and boundary integral equations for 3D anisotropic thermomagneto-electroelasticity in engineering analysis boundary elements. So heat conduction in a body with thread like inhomogeneities was performed in the following way. Assume we have fiber and we have an inclusion, the fiber like, so we have a point inside with on the medium line L, we have X, and we have a point on the surface X prime. Here we have a radio rho, and we have here a normal vector. So, and we assume that theta, the temperature at x prime x, is approximately equal to theta at xy. So we have here this integral, definite integral, equals 0, and from this we want to find the temperature at point y by using this equation 3, and the influence function gamma of x can be obtained using the equation 4. Heat conduction integral equations. So from this line integral, we obtain this integral equation, and for isotropic, here we have b at x0, and it can be found as a line integral of theta x x0 dl of x. And for isotropic and anisotropic materials, this parameter equals to beta at x0 is -1 over 4 kt, and is independent of spatial orientation of the inhomogeneity. So here we have, in this figure, you can see the integration rule for this special integrals. Now let's consider thermoelasticity integral equation. We have ui at x0 that is expressed with this integral equation. And the body is similar to the previous example. So modeling of thermoelastic thread-like inhomogeneities, we have heat conduction by using this equation and thermoelasticity by using this equation. Solution of the obtained equations. Influent functions are thought in the form of Legendre series. Pi of x are the Legendre polynomials. Heat conduction homogeneity models is as follows. And using these assumptions, boundary integral equation is reduced to the following linear algebraic equation. This is written here. The solution of the obtained equation. So model of a thermoelastic inhomogeneity is expressed via this equation, and boundary integral equations are reduced to the following linear algebraic equations. So we linearize our equations. So property contribution tensor heat conduction. So is expressed via these equations, and property contribution tensor of elasticity is expressed via the following equations. Fracture criterion. Given that the influence function of the inclusion is the integral of contact stresses along the perimeter normal to the axis of the inhomogeneity cross-section, the value of the body inclusion boundary can be associated with these influence functions that reach certain critical values in specific areas near the end of the fiber inhomogeneity. Consider that the detachment of inclusion occurs in most cases through a shear mechanism. The value criterion of a body with the fiber inclusion can be expressed as follows. So we have here fracture criterion. So assuming that the influence function is in the form of Legendre series, like this, sum from j from 0 to n, di j of x is tilde. The fracture criterion for line inhomogeneities can be rewritten in the following way, and evaluated the integral one obtains this expression. So assuming that delta over A is greater than 0 and far less than 1, consider criterion reduces to this expression. Thus, the obtained fracture criterion is completely defined by the thought influence function. In other words, its expansion to Legendre series. Or alternatively, we have this expression. Numerical examples. Temperature and displacement fields near a region non-deformable thread-like inclusion were modeled, and we got these figures, the solutions. Another second numerical example is influence function of conducting non-deformable inhomogeneity. So we have here these normalized functions, distribution of these expressions, and final example is influence functions of conductive deformable inhomogeneity were derived and depicted on these plots. Here we have effective properties, the plots of effective properties. And thank you for your kind attention.